thanks for the organizers again for organizing this wonderful workshop. It's very interesting. Really, every day is more fascinating than the other. Of course, in increasing order, because this is my talk. Okay, on the last day. So, and thanks also for accommodating me and moving this talk to another day. Okay, so I want to talk about fully scalable MPC algorithms. So this is something that was discussed before, for clustering problems in high dimension. And this is joint work with Arthur Chumai, Ruichen Gao, Xiaofeng Jiang, and Pavel, who just spoke before. Okay, so basically I'm going to talk about the same clustering problems that Pavel discussed before. So it's a K-median, and illustrated here, we discussed it, and facility location. As you know, these two problems are related. So here the number of clusters or centers is not restricted to be k, it's just actually a penalty function. And just know that facilities or centers is like the same, different words for the same thing. And I'm going to use the notation that P for the points in the data, C for the centers or facilities, but I'm going to use the word centers probably more, whatever, interchangeably. Now in both problems, I'm thinking about the scenario where points are in RD, and the centers are also taken from RD. So not from a graph or anything. However, by some simplification or without loss of generality, you can assume that the centers are actually coming from the point set, from the input. This is up to factor 2 because of triangle inequality. Very simple, up to factor 2 in the cost. And we're going to do order 1 approximation, so factor 2 is acceptable. And another thing is that there's a cost for opening a facility F. I'm going to, by scaling, assume that it's just going to be 1 because we're talking about RD, so it's the same as the previous talk. Good. So we want to look at different sublinear algorithms, and this is like the motivation, so you all know it, but we're looking at different modeling aspects, trying to understand modern architectures, how to design algorithms that are efficient, and there's like streaming, etc. And I'm going to talk today about massively parallel computation, or MPC algorithms. And the techniques are sometimes overlapping, as you'll see in a minute, and sometimes you need new techniques between different models. I mean, like MPC, streaming, sampling, etc. So let's talk for a minute about this MPC model. It was introduced or discussed 2 days ago, or 3 days ago by Mohammed. But let me repeat it. So it's a theoretical model that captures something, a lot of practical systems that are actually deployed very broadly. I'm going to use the following notation. So n is the input size. Now they have machines. You have a large number of machines. Each one has space S. So you can see it in the picture. These are the machines. The input is fed to machines of space S. The number of machines that you have is, let's say, M for number of machines. The critical issue here is that every machine has space which is only n to the epsilon. So it's much smaller than the input size, but it's not too small in a way. Okay, so and then how the computation works is that you have these rounds which are synchronous. Inside the machine, you can do whatever you want, any computation. It's completely free, which is, impressive, but it's actually useful abstraction. And the bottleneck is really the communication between the machines. Because this is local, it makes sense. The expensive thing is actually to shuffle the data between machines. This is the modeling assumption. So these are the rounds, and local computation is free. Then you have communication. Every machine can talk to every other machine. That's not a restriction. The real constraint is that if a machine has space S, the total communication going out or into a single machine is also S. Okay, so that's the bottleneck. And the goal is to minimize the total number of rounds, like the running time, if you wish. If you think of the parallel machine, the running time of the algorithm or the number of rounds. Another important but secondary goal is the total memory, so it's S times M, because you have each machine time has space S and M machines. So you want it to be small, but this is sort of like secondary. And of course, this has to be at least N, right? Because initially, just to store the input, to split the input of size N, you need S times N to be at least N. Good. So we want to look at MPC algorithms, like in this model, for clustering problems. What can you do with this MPC model? So here are like a few basic things, because I assume many of you have not seen this model before. So it's like one slide, 101 on MPC, primitives, things that you can do in MPC. So one thing is broadcast. You have one machine, one message of size n to the epsilon on one machine, You want to send it to all other machines. Okay, so what do? Just in one round, the first machine sends it to n to the epsilon different machines. Okay, so I'm cheating here with the epsilon, I'm assuming the space. S is actually n to the 2 epsilon. So you have a message of size n to the epsilon, you can send it to up to n to the epsilon other machines. So it's like n to the, and then each machine sends to n to the epsilon new machines. So maybe these are like the first n to the epsilon machines, then new machines, etc. So it's basically a very simple binary tree, not binary, complete tree. And the number of rounds is log to the base S of n, order 1 over epsilon. And the way we think of it is that this is order 1 many rounds. So think of epsilon as fixed. It's all generalized, but for simplicity, epsilon is fixed, so this is order 1 rounds. This is a very, very fast algorithm. The goal is to get order 1 rounds and not, say, log n rounds or, God forbid, log n rounds, which is much worse than 1 over epsilon. Okay, so this is our goal here. And this is called fully scalable exactly because this S could be any n to the epsilon. So you can scale this, the size of a machine to be n to the epsilon for any fixed epsilon. That's the name of the model, fully scalable. Okay, there's also like other operations called in the literature converge cast, which is basically the reverse. You have information at the leaves, and you want to all send it to the root of the tree. Of course, if there's like 2 different messages, you cannot send all of them to the root. So basically, at every node, you just sum up or something. You do something like XOR or summing or some operation, and then it works the same way. Another very useful operation you can do is sorting. If you have n numbers and you want to sort them, then this was shown how to do again with space, with number of rounds log to the base S of n. You can sort these numbers, and also you compute the rank for every number. And moreover, you can actually move them away, shuffle the numbers so that the first machine, say, holds the n to the epsilon smallest numbers, the next machine, the next n to the epsilon smallest numbers, etc. Okay, so as I said, the goal is to get order 1 rounds. Now, I've been asked before about what's the difference between this and Pira. Okay, so because there are some similarities and some differences, I think the main difference, so there are like several small differences. The main difference is that we said that a machine can do locally whatever they want, like in order 1 time, in 1 unit. Okay, this is like a magic assumption. This changes the whole perspective that we were trying to get to order 1 round. In Pira model, usually you actually count these operations, and then consequently you want a lot of small machines that have very little capacity. And what ends up being is that basically every computation at best takes polylog n many rounds. And then if you're already paying, log to the cubed or log to the 6 many rounds, parallel time, then, okay, maybe you're trying to shave off these logs. But if you're trying to translate this back to this model, you're not going to get order 1. Maybe you can shave some of the logs, you're not necessary. But you're not going to get order 1. Okay, like out of the log to the 6 many rounds, maybe some of them are not necessary, you'll get 1 log or log squared at best. Okay, so it's not like the Pira results that are known for similar problems apply here. Okay. Okay, so now our results are really MPC algorithms for clustering, facility allocation, and k-median that I mentioned before. We're going to simplify something that the dimension is up to order log n or smaller because of the JL lemma, and you can actually implement the JL lemma in this MPC model. It's not difficult, but then you have to put all these parameters, the d everywhere. Since I'm assuming d is small, it's only poly d factors like polylog. It's going to be absorbed in the n to the epsilon, so I don't have to write them explicitly. Okay, and the real challenge for clustering is that the algorithms must be local. Local in what sense? A single machine can only have space S. So it cannot even have like 1 bit per cluster, per center. Just understand the clustering, sort of like you need k center points. Like if you want to use a very frequent, very powerful tool called coreset, coreset is something that basically represents your data using roughly slightly more, but let's say even ideally using k points. Maybe k over epsilon squared or something like this, or tilde k. So you need at least k points. But you don't even have space to store all the k points in a single machine. So a single machine sees sort of like very limited view of the data. And we like overcome this goal and design MPC algorithms that do have order 1 round. So again, order 1 here is like what I called before, 1 over epsilon. Okay, that depends on the space, so I'm omitting this notation. And the total space is slightly more than linear. Okay, that's slightly not optimal, if you wish, total space. And these algorithms we have two algorithms for facility allocation and for k-median. For facility allocation, the approximation is order 1 over delta. So you can think of it as like we're getting order 1 approximation. We have to play a little bit in the total space, but other than that, we're getting order 1 approximation. For k-median, we get the same approximation, but it's not an approximation algorithm, it's a bicriteria approximation. And the number of centers that the algorithm finds is 1 plus delta times k, like 1.01 times k, as opposed to being exactly k. So that's not what's called true approximation of bicriteria. Another nice feature of this approach that extends to k-means. So k-means is like k-median, but with the square distances and stuff. So some algorithms for k-median do extend in the literature in general. Some do not. And these ones do extend very easily, so we solve it in generality. And the way we solve it is actually by using the facility location and sort of like the Lagrangian relaxation. So we use it in this method. So the base idea is to use the facility to solve the facility location problem. Now, just a comment about prior work. There was a little bit of work on clustering in the MPC model. Basically, there are like 2 or 3 papers about this. Most of the work on MPC algorithms was actually on graph algorithms. And we're talking about problems in RD. Okay, so most of the work is on graph algorithms. There's like tons of papers on MPC by now. But on points in RD and clustering, there are basically 2 papers. Both of them achieve only polylog n approximation. And we're getting order 1 approximation for, let's say, for k-median. These papers are for k-median. Okay, but one of them, okay, I'll talk to it at the end. One of them is actually a true approximation. The other one is also bicriteria, but even worse than 1 plus delta, and et cetera, but doesn't extend to k-means, and so on. So, okay. So let me tell you about the facility location. That's going to be most of my talk, and I don't have time to speak about the k-median. Okay, so the base algorithm is something that Pavel mentioned before. This is Metup-Plaxton algorithm. So their algorithm, they designed it as an offline algorithm to give 3 approximation for facility location. And basically, it computes for every point in the data, this critical radius RP, which is between 1 over n and 1. Because the 1 here is because we assume the opening cost is 1. And then there are like, Then their algorithm, the way it works, is very sequential. It says basically you scan the points P in non-decreasing order of RP. Okay, so you have to scan them in a particular order. And then for every point, if you don't see within the radius twice this critical radius, you do not see any open facility, any center that you already decided to, any point you decide to make it into a center, then you open this point as a center, and you scan sequentially. So of course, every decision that you make in one iteration may affect later iterations. Okay? And they show that this achieves like 3 approximations. So it's a highly sequential algorithm, and we want a parallel, basically, algorithm. Of course, there's another step that is hidden here, is to compute these RP values. And as Pavel mentioned before, basically, if you don't care about computing the value exactly, but only up to order 1 approximation, basically what you can try, you look at all these balls of radius r, but r is only a power of 2. So only logarithmically many different values of r. For each one, you need to count how many points you see within this ball. And when it reaches this trade-off that within radius r, you see 1 over r many points. That's your radius, like the smallest r that works. So that's basically like a counting problem. And this is sort of like well understood from this paper of Badui, Chumais, Indek, and Zoller. And really, this approximation suffices for all purposes. Okay. So this seems to be like more amenable to parallelization, because this is like you have log n different radii r, and you want to do it for every point in parallel, and then take the minimum. So this is sort of like seems more parallelizable, but this is highly sequential. Okay, and these are the properties that Pavel mentioned, that, for example, the sum of all the RPs is basically a good approximation to opt. So this is what you're trying to compute. However, unlike in the streaming algorithm that Pavel mentioned, like in the previous talk, we don't want just to compute this value opt. We actually want to compute a solution, like decide on the facilities, or if you want also on the mapping of each point to nearby center. Okay, so for the streaming algorithm before, which was very low space, it was reasonable to only expect to compute opt. So you're like outputting one number. Here now we actually want to output a solution which could be of size up to n. Okay, so the solution from there is like not enough. Potentially you can apply the streaming algorithm in this MPC, but it won't be enough. We want to actually solve, actually output a solution. Okay, this is sort of like illustration of this first property about the ball. So let me skip it. Okay, so we can achieve this order 1 approximation for facility location by this strategy of first we have to estimate these RP values. And now, so this is basically what I told you before, easy to parallelize relatively. And this is like the same as before, but now it's the difference from the algorithm of Metto and Claxton. We're going to do this 2 steps. So the first step, for each point, we just draw a random value. I'm going to call it a hash value. It's not really hash, just a random number, really random number. It's convenient to call it like the hash of this point. H of p, just a random number between 0 and 1, uniformly. And we're going to use it in a minute. And now for every point, we have to decide whether to open it as the facility. The idea now is not to do it sequentially, do it in parallel. So you're going to decide for each point, sort of like looking at very, very limited vicinity. What we do with using 2 rules. If one of them works, we open it as a facility. One, you open each point with probability RP independently of everything else. Remember, RP is a number between 0 and 1. So that with probability RP, we say, oh, this is a facility. We open it as a center. Second rule is more interesting. We look at these hash values. And if this point has the minimum hash value around its vicinity, and this vicinity means a ball of radius, okay, so this is supposed to be RP, the same critical radius for the point. It's not a global radius. For each point has this critical radius. We look at the critical radius around it. If that point says I have the minimum hash value, say, okay, then I'm like the chosen one. Okay, so you open it as a facility. What's the intuition here? And I'm going to show it in the next, by picture in the next slide. This is designed for 2 extreme cases. These 2 rules are designed for 2 extreme cases. When the optimal clusters intuitively could be either highly overlapping for the first rule or completely disjoint. Okay? Maybe it makes sense if they're like completely disjoint and you have like something like in a ball of radius r, you have 1 over r many points. One of them will have the minimum hash value. That one will be open as a facility. And everyone will say, oh, we agree. That one should be the facility. So they're sort of like highly coordinated or synchronized in this way via this hash value, minimum hash value. Okay, this is sort of like a well-known idea in different contexts, other contexts. Okay, and another thing to watch, to pay attention here, there's a very simple observation. What is the probability to open every point P as a facility? Okay? Because this is going to be like the total expected cost. So each point is opened here with probability RP, okay? What happens here? Well, we look at the ball of radius RP. The number of points there is about 1 over R. To be the minimum is like 1 over R, 1 over the number of points. So it's also RP. So in expectations, you open like a point with probability big O of RP, and the total number of facilities that you open is just summation of RP, which is like opt. Because each opening costs you 1, right? So the total opening cost for the facility is 1 times the number of facilities that you open, and I just told you what is the expected number of facilities that you open. You also need to analyze the connection cost to connect to these centers, right? In facility because you have 2 costs, the opening cost and the connection. The opening, I just told you, it's like immediate. The challenge is to analyze the connection cost. So here is like the picture. Suppose you have these joint clusters. Okay, this is like the easy case. I told you before, maybe even on the line. It could be more generally, but even on the line. You have something like, in radius R, you have something like 1 over R points. Far away from this, in radius R, you have 1 over R points, etc. What will happen in each point, you sort of like, think of it as a ball. One of these points will have the minimum hash value, and that one will be chosen as the center. You open roughly 1 out of this 1 point in each ball. That's exactly what you want. Okay, that's one extreme case. This is sort of like the easy because it's a really idealized situation. The other simple situation, if you have overlapping clusters. Okay, so let's see in a picture, suppose you have this ball here, and I'm drawing it even on one dimension, but of course, in high dimension, it becomes even more severe. So you have this ball, maybe like here, and you say, oh, where's the minimum? Maybe it's here. But this point says, well, where is my minimum? Okay, because it's like say the points, this is point of same radius r, which means the same capacity of number of points inside is 1 over r. And these similar balls. So each one has like another minimum, sees like another minimum and another minimum. And then basically no point here is open as a facility. And then potentially the closest facility is actually sort of like gradually becoming farther and farther away. So this is a probabilistic event you have to analyze. And it could become even worse if the radii here are increasing. And then it's actually this point that you're saying, oh, where is my closest facility? Well, it's not here, but maybe it's here. Oh, no, but maybe what about this one? And it's sort of like getting intuitive when you're analyzing it, getting farther and farther away. Okay? So this is not good for the min hash rule, but this will be solved by the other rule. That's why we need the other rule. Okay, sort of like an expectation, and you have like a constant probability to have somebody open in this ball. If it doesn't happen, then with constant probability you have in the second ball, with constant probability you have in the next ball. So now it's not going to last for too much. Right? Like I said, probably 1/2 or something. So yeah, an expectation is not going to take more than 2 iterations, ideally. Okay, so for the analysis, remember the cost is connection plus opening. I told you about the connection, so this is just written here. That's what I told you before. The connection cost is the one that is more involved. Basically, the idea is to think about this as an assignment path. So you start with a point P. I'm going to call it just P0. So where is the min hash? Well, maybe it's a point P1 nearby. What about P1? P1 looks at the radius around it and looks at the min hash in its own ball. Says, oh, the min hash is actually some P2, and you keep going. And basically, you stop when you get to a point PT that is an open facility. Okay? Yeah. So informally, each step is likely to reach a facility. Like if your point PJ sees if you see few new points, like basically the next ball is almost overlapping perfectly with the previous ball. So you see very few new points. Then the min hash is almost the same. This is almost like having the same ball. So you want to sort of like rely on this rule of like S2 where it's like the same ball. And if the balls are sort of very different, you have enough new points. Each one has fresh probability because of this other rule, which has independent coins, not the hash value, the one that is independently opening. So having many new points means like you have many chances for opening facility somewhere in that ball. So either I get to PT, which is itself a min hash value, or around it there is one of these independent points that were opened as a facility independently. So basically, I'm not going to go into the analysis, but basically you have to balance these two arguments, which exactly is what I wrote here is the key argument. You have to count this number, and it's like the complement number, and one of them has to be large, of course. And the other thing is that every step that you make, you go farther away from the P0 over here, but by the triangle inequality, you can, of course, bound how far you go. So I found a facility like T hops away, which intuitively is like T times R. However, it's not the same R every time. So that's like an extra complication. You have to take the R value, the radius that each point sees. So that's like an extra complication, but of course, in the analysis, you have to worry about, right? This is like, each distance is like R of this current PJ, and maybe these values are not all the same in the sequence. Okay, so basically the argument there is a little bit involved to balance all these things, but it works in expectation, of course. Everything is about the bounding the expectation of a single point to see a facility around it, an open facility around it. Okay, so one other aspect that I want to talk about is this geometric aggregation, which is needed for this parallel implementation. And this is even just to compute these RP values. I claim that it's very easy to do it in parallel. Okay, let's see if it's really easy to do it in parallel. So if you have these points P, let's say even you have just one radius R, they have log n values, all the powers of 2. Let's look at one of them. and I want to look at some function. Let's say this is just like, you see it a bit, like a function like counting. You're given a set, you just count how many points there are. This is something that I need because I want to count how many points are in a ball. The other thing that I need, there are only two operations, is if you get a set of points, I want to know just give me the minimum hash of this set of points. Okay, so these are the two functions I care about, G, so to be specific. And now basically for every point, I want to say, look at the ball of radius R and evaluate this G, either counting the number of points in the ball or the mean hash value in this ball. Can I do it in parallel for all the points simultaneously? Okay, because we have this parallel machine. So basically, the facility location algorithm boils down to just applying this a few times. To compute the RP, then to use the RP values. It's just all these using this. Because, I mean, S1 is just independently operating facilities. That's trivial. And the other one is basically something like this up to, well, I use a uniform R, but you need to use different R each one. OK, that's the same. So how are we going to achieve this? So there's an easy way if you're willing to use total space n squared. Basically, since you have all the points, in some simple operation, basically create like a record for every pair of points, like P comma Q. So that's going to be n squared record. You sort of like make sure they're somewhere in your big overall machine, like the MPC. And then you sort them in the right way. And then you can see basically like all pairs where P minus Q is at most R. Right? If you sort it correctly, then you can count, like apply this thing. Like for every P, you sort all the QD points by their distance. So sort of like it's just sorting. So this uses space n squared. And what we are able to do is actually do it in space, which is n to the 1 plus delta, as I promised. Okay? And this is using something like the following, which relates to the talk of Pavel and Arnold before. So I'm going to need some assumption about G, which is something decomposed, where you can compute the G of this joint union if you know the G value for each step. So for counting, it's trivial, right? Because you just add up these counts. And for the mean hash, you just apply the mean of these values. Okay, so for such functions, we know how to do this. And the idea is, the theorem we prove here is like this. There is an MPC algorithm in order 1 round, and this total space, that for every point, computes this G, not on I wanted to compute this G on a ball of radius R. Instead, I compute it on some set that I have no control over, some set A, not a ball, not B, but A. They sandwich between a ball of radius R and a ball of bigger radius R over delta. Okay, so there's like some slack. So it doesn't have to be a ball, but it's like sandwiched between two balls, something like this. There is the ball that I want. There's like an extended ball. You want to compute the G on the ball. Maybe it's OK to get G on the bigger ball. What I can really get is G of some undetermined set sandwiched in between. And because it's sandwiched in between, it's sort of like approximation. It's good enough for our purpose. And the way we really do it is by using these sparse partitions or consistent hashing. And this is sort of like the picture. And yeah, I have to apologize here. I forgot. I noticed that I forgot Arnold in this reference, but it's that paper that Arnold mentioned, talked about. That Pavel talked about. So the idea is like this. So I want to count how many points I have in this ball. This is really what I want. I have this sparse partition, so it looks like, okay, I drew it like sort of like a square or something in this picture. This ball only intersects a few, I think you call it tau, of these cells. Okay? So basically, I'm going to count all the cells that intersect this green ball that I wanted. So I'm going to get, let's say, counting. I'm going to get the count from here, the count from here, the count from here, the count from here. So I'm going to approximate this ball by this shape, which is sandwiched inside the other ball. Okay? That's basically the high-level idea. It's very simple, and the intersection here is important, like the number of tau of intersection is important. Okay, so anyway, we have to use this sort of like technology from there. Yeah, basically when you have all the points in this cell, you actually map them to one representative, like say the lower left corner or something like a center point for each one. And then if you do sorting, they all get bunched up. You can easily count them. Okay, you have to do locally. You map them like lower left corner. And then for each point, and then you do sorting, they'll all get bunched up into one machine or something like this. Okay, so that's what I wanted to say about K-median. I said I'm not going to go into it, but it uses the FL approximation, and then some other tricks, somewhat semi-standard, like weak core set and averaging arguments to go. The difficulty is to get into 1 plus delta times K. The number of centers that we open is not like 2K or 100K. This is sort of like relatively easy. To get to 1 plus delta K centers, that's like most of the work. And then we have to use the same arguments from before, like S1 and S2 that we did in this parallel. Similar arguments and similar this geometric aggregation that I just mentioned. Okay, so to conclude, yeah, I think there's a major open question how to get true approximation for these problems. Basically, what for K-median, as I hinted, there's a polylog n approximation is known. We get, for K-median, right? We get order 1, but it's a bicriteria. For K-means, even this is not known, like this polylog true approximation. And another question is like, do you really need this space n to the 1 plus delta and not something like n O tilde n, like n times polylogs? I don't know if that's true, but it seems to be inevitable because we see similar trade-off for another problem of MST and another work on MPC. So maybe it's really necessary for high dimension. There's some indication, but we are not really in good shape to prove lower bounds for MPC algorithms. So at the moment, it seems like widely open. That's it. Thank you very much.
Time for a question. Okay, well, let's thank Robbie again.